All right, so now let's go back to that 4D problem. So I'm so glad that it is something that we have some research on, because it's something to me that was immediately fascinating when I read about the AlphaFold 2 successes earlier and how it had done so well at predicting 3D protein structure. In my mind, then I was like, well, yeah, the next big problem to solve then is going to be computationally much more complex, is going to be this 4D problem of how does this 3D structure change over time as it receives the antigen that it binds to, or as it does. And I guess that's specific to antibodies, but as the protein does work, how does its shape change?
So this is one of the interesting things, actually. Antibodies are one where if this is not so much of a problem. Well, we don't know that for definite. I should be clear here. All of the evidence suggests that antibodies, when they bind to their target, when they are very affine, so when they bind strongly, which is when we're interested in them, their shape doesn't change very much at all. Yeah. So, and the reason for that is sort of pure physics energetics. So if you have to change a lot on binding or have to fix your conformation on binding, there is usually an entropy cost for doing that. So if you're rigid and already in the shape you need to do binding, it's easier to have, a higher binding energy because you're losing less energy to do the binding as well as that which you gain. Whereas there are examples of other proteins which do change. Now, there are some antibodies that do change on binding, just to be clear, and it's not completely like a jigsaw piece. So some of it is moving, the side chains will move, there'll be changes in conformation. But interestingly for antibodies, that actual change in shape is for things that are strong binders, it is thought, because we don't have complete evidence, but it's not so much of a problem.
Nice. Okay, I got it. Well, it's still it's still interesting to me that that this will be as you said, people at DeepMind, and I'm sure in other groups, are thinking about this 4D problem and how we can be adapting algorithms to be able to handle these shape changes. I guess we keep being surprised by how quickly problems get solved. But maybe that's one that'll take a few years.
I think, it's been amazing over the last few years how quickly all these types of problems have been solved. And I think one of the interesting things here in terms of a lot of this is thinking about, what problems we could still solve where we actually do have, if you like, the data that would allow us to solve it, as well as, it's a well-formulated problem. And it's the way to think about it is where DeepMind showed their first success was on games. And the reason they picked games, and they're very open about this, is because games are a multi-optimization problem. That's what machine learning is really good at, with well-defined rules. Machine learning likes those. And with a way of being able to generate or have lots of data that describes the entire space you're going to work in. And so it's interesting to think, particularly in terms of, drug discovery, biologics, but also in all sorts of other areas, what problems fulfill those requirements? Because many that we would like to do don't. And so then it becomes either we need very new techniques to solve them, or we need to think, how do we define the rules such it would be helpful? That's usually the biggest problem, the rules of the game. Or the data is the other really huge problem that people miss out very frequently here. Actually, the volume of data required, and it's not just lots of data, it's data spread well across the space you want to search. If you only have data in a tiny area of the space, none of this will work. It doesn't. It's very difficult for it to learn the rules over here, miles away, if I've only got data just in a little circle around a tiny point over here.
Yeah, I see what you're saying. And then so, we obviously need really good training data for any of these models to be possible, and to have really well-defined data to work with on these 4D problems would be very hard to come by and extremely expensive to create.
Yeah, and I think people will think about other ways to think about that. So you might use lots of simulated data from using physics simulations, for example, or other ways to attack this. So it's like you've got to think about what machine learning is good at, if that's if that's kind of your preferred hammer, and then work out, can you set the problem up such that a hammer will work, or are you just, no, don't use a hammer right now, think of something else.
And there's probably some way that I'm thinking about this incorrectly, but I imagine in a situation like that where you're trying to do physics simulations of 4D structure. Of course, if you could do those physics simulations perfectly, you'd have already solved the problem. So
that is almost exactly it. That is actually a phrase I use quite a lot when people go, well, it's all right, we'll run the simulations and then we'll train the machine learning model to do them. And I'm like, well, if the simulations worked, I wouldn't. I mean, you still might train the machine learning model because it might be a lot faster. So you can make an argument that that's a good thing to do because it's much quicker. But if you know that the simulation is incorrect, you have to decide, is it worth training something that gets to me the wrong answer much faster? Right. Or is it correct enough that I might be able to use it to help me generate the types of data that will make good models for doing this kind of thing? So there are kind of positives I can put on this, but it's a bit more nuanced than just, if you can simulate it, then you could train it and then we'd answer it. As you say, if the simulation's wrong, it's not quite clear what you've trained yourself to do.